In this video, we'll talk about a problem in the Putnam Mathematical Competition 2005. The problem states that P denotes a polynomial with real coefficients in the variables x1 through xn. And suppose that if we apply this differential operator to P, d by dx1 squared plus d by dxn squared, this expression is identical to 0. And that x1 squared plus xn squared as a polynomial divides this polynomial P. Then show that P is identically 0 itself. And now let me present the solution due to Richard Stanley. For simplicity, we're going to use the following shorthand notations. Let x with an arrow denote the array x1 through xn. And let nabla with an arrow denote the array d by dx1 through d by dxn. Now suppose P of x, here we're already using this shorthand notation. This literally just means this P of x1 through xn. If this is equal to Q of x with an arrow, times x1 squared plus xn squared. Suppose P of x can be written as Q of x times this x1 squared plus xn squared, as is assumed in the problem. So this assumption in the problem. Then we're going to replace this x with this nabla times, when we make this a replacement, this x1 will be replaced by d by dx1 and will be squared all the way to xn replaced by d by dxn squared. Maybe let me give you one more example. Say if this P is x2 cubed plus x3 times x5, then P of nabla will be d by d x2 cubed plus d by dx3 times d by dx5. Also here, don't worry about the order of taking differentials, because we are living in the world of polynomials. It's okay that you change the order of those differentials, because polynomials are smooth enough for you to change the order of taking differentials. Okay, now let's move on from here. Let us apply both sides to the polynomial P. This differential operator applied to P of x, and this product of different operators applied to P of x. The right hand side. What do you see from the right hand side? From right hand side, combined with this hypothesis, you get identically 0. So this polynomial of this nabla applied to this polynomial itself is identical to 0. And we want to conclude from here that this polynomial itself must be identical to 0. To this end, we will let p of x to have the following expression. Where this alpha is a shorthand notation for the n array of 1 through alpha n, with each alpha sub I a non-negative integer. Then p of nabla will be correspondingly the same sum, just with x1 through xn replaced by d by dx1 through d by dxn. Now we go back to look at this equation. In particular, we're going to look at the constant terms on the left-hand side, which are supposed to be 0. Now there are many summands in p of x, and same for p of nabla. The key observation is that the constant term in p of nabla applied to p of x appear precisely when d by dx1 raised to the power of 1 product all the way to d by dxn alpha n meets x1 alpha 1 through xn alpha n. This is like in physics, when a matter meets its inverse matter, they will be neutralized. If that is very unfamiliar to you, you can go back to watch the movie Tenet, in which this idea of neutralization is really amplified. But here I just want to emphasize, this is precisely the case where we could get the constant term. In any other case, if the n array of 1 through alpha n is not equal to bit 1 through bit n, then this application will either give us 0 or some non-constant, say some monomial that is not equal to 0. So this is precisely a case where we're going to get a non-zero constant. In the theory of polynomial, of course, we do not call 0 as a constant. And what happens when this meets this? This will give us 1. So the constant term in here is the summation of C alpha squared. But you know from star that the summation must be 0, because C sub alphas are all real constants, which forces each system of alpha to be 0. Hence, P here must be 0. And we are done with this proof. But I would like to add a remark. Let me make a remark here that what happens if instead of looking at a real polynomial, we look at a complex polynomial. For complex polynomials, we can get the same result. By replacing in the proof P of nabla with its complex conjugate. To take this complex conjugate, we simply take the complex conjugate of each C sub alpha. And we get, instead of squares, C alpha conjugate times C alpha equals 0 when you take the summation. And this part, is just the modulus of C sub alpha squared. So we still get each C sub alpha equals 0. And we get P equals 0. Same result.